I am a venture partner here at Contrarian Ventures, and I'd like to welcome all the startups to this live New Energy Challenger pitch. And I'll be moderating the session today. So I'd like to introduce two judges. I've got with me Stephen Mearsman, who's the founder and CEO of Zenobē Energy, and also Jesse Tiedemann, who's the investment manager at Chevron Technology Ventures. So thank you, Stephen and Jesse, for taking the time to be here. Thank you. And I'd also like to thank everyone and all the startups who've taken the time to apply so far. I appreciate it was effort to get to this point, but thank you for your participation. So just some background on New Energy Challenges. I know you guys have been through the rigmarole to get through this process so far, but for those who are watching live, New Energy Challenges is an initiative that we set up at Contrarian Ventures that brings together some of the top energy talent covering Enertech, transport, sustainability, all in one place to compete for a cash prize, and also the attention of global investors, both financial and strategic. And in total, we have 75 CVCs and VCs who have poured over these decks and will be providing capital to this initiative. We compete in 6 main tracks. So we're looking at batteries, hydrogen, e-mobility, digitalization, automation, and AI, and future grid. And you are you are part of the cohort of 60 finalists who have got through 10 each track. You've already been through a panel and been chosen. This panels consisted of venture capital, ecosystem builders, it's the green media, and as well as leading participants from large CVCs and corporations. Once this stage is over, there will be 30 companies left in, 5 from each track, who will hopefully be pitching live if and how coronavirus pans out in a 2-day event, which is Energy Tech Summit 2000. This may happen live, it may happen virtually. Hopefully we can have a live event. And ultimately, it's going to be one winner takes all. There'll be one winner of the New Energy Tech Challenge, and one cash prize. So just in terms of the format of today's session, there's going to be a 5-minute elevator pitch from each company, and you'll get 4 minutes of questions from our jury. Given the number of participants today, I'm going to be pretty succinct on timing. So please forgive me if I interject at certain points, because we need to keep the session moving. So with that, I'm going to introduce the first startup today. This is Acceleron from the United Kingdom, and I'm introducing Carlton Cummings, the co-founder and chief technology officer. There he is. Hi, Carlton. Please share your screen and share away.
All right, just checking you guys can see my screen. So it just did this thing where it put the presentation on screen 2 instead of screen 1. Anyway, I'm just going to run it as it is right now.
We can see you.
Yeah, I'll just run it as it is right now. Keep it simple. Right. So Acceleron, we've come with the idea of creating a battery for life, and that's been a really key ethos for what we. All right, let me make a switch here then.
You can just, if you go back to that, you can hit the 3 dots and turn off the presenter mode.
Yeah. Here. Good. There we go. Should be exactly as it's supposed to be now. Yeah?
Good.
Perfect.
Fantastic.
Let me know when we want to start the clock.
You can start.
Cool. At Acceleron, we've been focused in the energy storage space on creating what we call batteries for life. And that's a core ethos for us. And it's a lot focused on circular economy, making batteries in a way that everything else in the world tends to function organically. And what I mean by that, I'll usually give an example. When you have a car, for example, and something happens to it, you have a means of some sort of service that you can call to get things repaired. You know, there's a dealership, there's a service center, there's a mechanic involved, which makes sense because cars are usually very complex systems, and the probability of anything happening to break is quite high. So there have been systems created to maintain and manage cars throughout their lifespans. Unfortunately, today, that's not really the approach we have with batteries. Batteries are often treated as products with a very specific lifespan, and when they break, they must be disposed or recycled. There's no idea of being able to manage or maintain batteries on a large scale. And that has a lot to do with the design of batteries on a pack level. Most batteries were designed very similar models to how they developed them for consumer electronics, where they are assembled using permanent assembly methods, spot welding. Some of them will use lots of adhesives to bind components together, etc. And that makes it very difficult to retain any residual value at the end of life. It also makes it very challenging to manage and maintain them. The industry has taken one approach, which is to make the batteries last a lot longer, improving the chemistries, improving the materials we use to assemble them into packs. But fundamentally, developing a system where nothing is developed to be managed or maintained will generally have bottlenecks and oftentimes leads to waste. Many industries have proven that to be an example. It's the simple concept, if you were to build a car, you wouldn't rivet the wheels on because you know that's the highest probable chance of failure. So you'd want to make sure the wheels are designed in a manner which you can manage and maintain them, change them as they go. So what we've done at Acceleron is that we've taken an approach of sustainable design for the way the pack assembles. We position ourselves specifically not in the cell technology or on the product technology side, but on the pack assembly technology side. We're looking at revolutionizing the way we assemble batteries to basically create a hardware that has sustainability in mind, where it is designed for, one, full maintenance. You can repair, reuse, recycle many of the components as well, and then data analytics. The three aspects here are mainly focused on being able to take a product, put it into use for the first life, have data analytics to identify how it is performing, when it's failing, where it's failing specifically, and then have the ability to maintain it as it ages, as well as upgrade. And I think upgrade is a really important aspect of designing a product that's serviceable, where the whole idea is that as technology improves, if you have a product that's designed for serviceability, it means you have the ability to upgrade. And with an industry like batteries, upgradability is really important. However, the way we assemble batteries today, in many cases, it's very difficult to upgrade anything within the battery because most things are developed with permanent assembly methods. So why would this be interesting? Now, the reason why this is interesting is that it allows you to kind of to explore some really exciting business models when it comes to batteries. Currently, we see a battery as a product and it's sold like a product. It's a very linear model. You produce it, it's sold, it's used, and then it's disposed. However, when you have a battery that's serviceable, it allows you to treat a battery more like an asset, where you can provide a battery sale and you can attach a maintenance contract on that, which can include upgrades. The customer is no longer locked into today's technology 10 years from now, because the battery has the ability to be maintained and upgraded. That's really important when you start thinking about large-scale energy storage activities, where those types of asset lifespans are 10, 15, 20 years. Another attractive aspect of it is it gives you the ability to do repurposing, where you can take batteries and reuse them for second life aspects and applications. So you get more reuse potential. And then the third business model, which is the most exciting, is the ability to not sell the battery as a product at all, but to sell it in a service model, where you actually provide the battery as a service, and it's, you pay for power by the hour, you pay for usage. And that's what the whole idea is about, where you're delivering energy storage in a service model. The concept of a battery for life is designed to be produced, used, and reused as many times as reasonably possible. I believe, if my clock is right, I've just
that was you concluded just on time. Well done, Colin.
I do try.
That is your time. I hand it over now to Stephen and Jesse, who I'm sure, particularly in Stephen's case, will have a few questions.
Sure.
Jesse, you want to kick it off?
Just one thought is that when I'm buying a battery, I have a performance profile and a use, an intended use. So I appreciate the full cycle benefits, the full life cycle benefits, but could you give us a sense of what you're designing for, what, kind of getting it high power versus high energy, what the intent is?
Yeah, that's a really good question. The presentation more spoke about the general idea, but in terms of applications, Axon has been mostly focused on batteries for stationary energy storage, power backup, renewable energy. These are applications which we use to frame where A, the customer relies on a battery to deliver a critical service, let's say backing up the data center. B, the battery application tends to have a very long service life. Let's say a utility application where it's backing up a generator or where it's serving as the buffer for the grid. That's a 15, 20-year lifespan. So strategically, Acceleron is not positioned in any consumer-facing or consumer electronics-facing applications. Automotive is not necessarily something we're looking at initially, though there may be some application for heavy-duty or heavy-goods vehicles where they do get fairly heavy duty cycles and fairly long service life is expected. Mainly focus on those areas where longevity is really important. And most of the time, the battery is used to deliver a critical service. So the battery is more seen as an asset.
So would you say then it's priced as a premium product compared to other OEMs?
Well, it's priced differently. So instead of looking at it just by price per kilowatt hour, it would often be priced on price per kilowatt hour per cycle. So that's where you would see it has to be attractive in that scenario. It cannot be priced as a luxury item because it's going to be treated as an asset. And most of the customer that will use these types of batteries will be looking at return on investment on their balance sheet. What we're doing is that we're front loading or adding a bit more cost to how the battery is designed, making it serviceable, but we're trying to include a better overall total cost of ownership by giving the customer the ability to easily service the battery, easily upgrade the battery, easily maintain the battery. And what that does is it reduces things like decommissioning costs when you need to replace a typical battery. If you're thinking about large scale, container scale, and you need to decommission a large system, there's a cost to that. Recommissioning costs are reduced because you can just service everything as it is in the space. And then it gives you the ability of being able to upgrade things as technology becomes available.
And how would you quantify that total cost of ownership benefit and over what period?
So generally what we tend to aim for is a 50% improvement in terms of the current TOC, and we usually will aim for a TOC when it comes to lithium iron phosphate technology, because that's the battery chemistry that has the longest lifespan right now. And it's often the battery chemistry that you find will be used in applications such as renewable energy, backup power, etc.
Okay.
And we've taken a really different approach to it. So instead of trying to find the God chemistry, so to speak, we're trying to build serviceability into it to extend that lifespan in a more tangible manner, because that's what you do with generators, that's what you do with a lot of other things that are used for service applications. You make them serviceable.
Thank you, Cullen. Stephen, we're at the 4 minutes, so hope you've got a taste of what Acceleron are doing. All right, thank you, Carlton. We're going to move on to the next presenter now. So now introducing Jenna King, CEO of, and I hope I pronounced it correctly, Aminot. Jenna, welcome.
Hi, thank you. You're very close. Amionics.
There we go. Thank you.
Okay, so let me go ahead and share screen.
Yeah, share your screen and over to you.
Great. So as Chris said, my name is Jenna King, and I'm the CEO of Amionics. And at Amionics, our goal is very simple here. We're essentially addressing safety of lithium-ion batteries, and we're doing it from the core of the battery outward. So we're looking at the individual battery cell. And our SafeCore technology, which is in the individual battery cell, acts like a circuit breaker or fuse. to prevent the battery from being the source of a fire. So a little bit about the company. We actually spun Amionics out of a company called American Lithium Energy. And American Lithium has been around since about 2006, and they address military applications. So they've been building batteries for the US military since then. You know, custom applications such as unmanned vehicles, laser weapon systems, and actually the SafeCore technology came out of a project that they were working on to develop a bullet-safe battery for the soldiers in the field. And they also were working on a Department of Energy grant at the time to develop a multifunctional safe battery for the EVs. The idea being, if you could develop a battery that's so fundamentally safe at the cell level, what would that enable you to do at the design of the EV? Could you now put batteries in places where you otherwise wouldn't because of safety issues? Could you get a further range because of that? So we spun the company out of American Lithium Energy to commercialize the SafeCore technology. And so our model, our business model, is a tech transfer royalty bearing license to the technology. So this is our team, myself, my COO, who is former VP of Qualcomm. Our founder is our CTO, Dr. Fan. On my board, I also have the former president of Qualcomm and the current president of QTL. So the problem, as everyone I'm sure in the room is aware, is, you know, with the proliferation of more and more lithium batteries, you're just going to statistically see more incidents of thermal runaway. And there are many existing, you know, safety tools, as we call them in the industry, to design safer batteries. However, as we've seen, they certainly aren't foolproof, and there is room for additional safety measures. Major causes of failure, of course, overcharge, internal short, and some external heat situations. And so this is what we're doing with our technology. So you're looking at essentially a cross-section of a battery cell. And so you have your current collector, you have your electrode material, your electrolyte, and your separator. And what we've done—
Jenna, I'll just say we can't actually see that slide.
You can't see this slide?
No, it looks like you have a layer over what you're presenting somehow.
Can you see any of the slides?
We're still on the cover sheet.
Yeah, we're still on the Series B financing. So.
Oh, that's strange. Hold on here. Let me try.
If you stop sharing and reshare.
Is it moving through them now?
Yeah, we can see it now, yeah.
Okay, well, let me just skip to this guy. This is the good one. Okay, so this is a cross section of our cell. And so you have your current collector on this side. You have your SafeCore layer between the current collector and the electrode material. And so when you have an event, so in this case, we're showing you an internal short where you essentially have a meltdown of your separator because the temperature in the battery has spiked so quickly, the separator essentially melts down at a certain point. And so what the SafeCore layer is doing here is it's essentially creating a non-conductive gap along this line here. And so now you're, rather than the current collector pulling the energy, which is highly conductive, the energy is going to flow along the electrode material. So you actually have the same amount of energy being released. However, it's just released slower. And so the battery doesn't go into thermal runaway. Okay, is it switching?
It is.
Great, okay. So the Amionics difference. So when we launched the technology, we really had a realization that in battery technology, there's a lot of promise and not a lot of proof out there. And so we really sought to validate the technology in multiple chemistries and multiple applications. So we've been working with companies, leading companies really in EV, laptop, power tools, cell phone, and smartphone to build prototypes of their cells with their materials in high voltage LCO, 622, et cetera, with our technology in it to show that it works and to show that it doesn't have an adverse effect on performance. So as a result of those evaluations, we call them, so we've actually signed 2 licensees, one of which we announced publicly was Stanley Black & Decker for power tool applications. And we're actually in tech transfer now with 2 leading battery manufacturers to scale up the product into their applications. The other great thing about this technology, there's no significant capital expenditure for the battery manufacturers. So they're going to use their existing equipment. The existing equipment that they're using to coat now is what they use to coat the SafeCore. We just add one step on the front end. Materials inexpensive and globally available.
I'm going to have to stop you very soon.
Yes, no problem. Okay, so market size, just one point here. We really believe that this is applicable, as I mentioned, to all form factors and chemistries. We focused on EV, but we think energy storage is a major a place for this technology to go and enabling technology for energy storage. So we did our previous funding, our Series A with Qualcomm. We're now looking for our Series B funding, 5 to 10 million raised, and it's really to expedite the tech transfer process and where we are now.
Good.
Thank you.
Thank you, Jenna. Stephen, Jesse, over to you. You've got 4 minutes of questions starting now.
Well, maybe if I kick it off this time around. Question around, you mentioned the tech transfers and no additional capex required for the OEMs, etc. But how invasive is it in their production process in terms of fitting that extra step in? Is that retooling or?
No retooling necessary. So essentially what we're doing is we're using the same equipment that they would use to coat their electrodes anyway. And so we're coating the SafeCore layer on the current collector, and then they coat the electrode material on top of the SafeCore layer. And so really the only thing that you're adding is an additional coating, but sometimes they're doing that anyway for other reasons. They do other coatings, which ours can actually replace some of those other coatings.
Okay.
Jenna, do you have any concern as you move toward more lithium metals that that the market size might be disrupted?
Yeah, so that's actually a great question. So interestingly, our partners go very quickly to next generation chemistries and whether SafeCore is applicable. And so, lithium metal, silicone, the new materials that people are looking at, this technology even becomes more important because some of those technologies are so volatile. And even with solid state, even though you're getting rid of the flammable electrolyte, what happens in solid state is you still have a massive rise in heat. And so the SafeCore fuse can actually limit that rise in heat. So even though you might not have a fire with a solid state, you still have a meltdown of your system. So SafeCore is still applicable even there.
And so your business model then is to essentially license to OEMs exclusively? Or not exclusive to each, but that's the exclusive business model.
Yeah, and interestingly, what we found is the market kind of told us that that's what they wanted. So they wanted to hold the license because they have multiple manufacturers. And so they didn't want to be beholden to one manufacturer. And so that's how we went down this road where we license and then they sub-license to their manufacturers of choice.
Stephen, any more questions from your side?
Well, I guess the question is on the competitive side. And I mean, in terms of, you mentioned the technology is really in the coating, etc. You've got these licensing deals, etc. And I guess the real barrier to entry for a competitor is the onboarding process of various OEMs. Is that right? Or are there other sort of significant moats that you build up that way?
Yeah. So from a competitive standpoint, our patent portfolio actually is quite robust. And so, anything where you're creating a non-conductive gap within the cell basically reads on our IP. And then of course, there's a lot of trade secret that goes into the formulation and design. And there's a lot of levers that we can, pull to get that design down. So I think that's the barrier to entry there. And then of course, to your point, we've gone through a massive amount of validation work with all of these partners to prototype, and we're very fortunate that we can build cells here in Carlsbad and prototype right here in our facility. So I think a combination of those two factors.
Jenna, can I cheekily ask whether you can share any names of OEMs that you're piloting this with, or is it?
Well, the only one that I can share publicly would be Stanley Black & Decker, and so that they're a big power tool company here in the United States, well, global.
Very good. All right,
but
guys.
I can say we definitely are working with, I would say, that the marquee companies that you all know very well.
Good. Well, look, I think we'll have to draw it to a conclusion there, but thank you, Jenna, for that insightful presentation. Sorry for the glitches. All right, moving swiftly on now to Fergal Harrington Beatty, I believe I pronounced that correctly. He's the Technical Sales Manager for Update Power.
Yeah, that's great. So, is this working for you? Can you see the main screen?
We can.
That's brilliant. Okay, I'll start. So yeah, good afternoon, everyone. I'm Fergal Harrington Beatty, and I'm actually just started as the head of automotive and aerospace. And today I'll be speaking to you about our ultra-high power cell. So I'll discuss the problems faced by the current generation of lithium-ion cells, our solution, our progress so far, and how our team plans to scale our business and deploy the UHP cell in volume in the UK and across the world, and how this represents a strong investment opportunity. So currently, hybrid vehicles in both the automotive and aerospace sectors are limited by the performance of lithium-ion cells, which have high internal resistances, making them prone to overheat when fast charged and discharged at a high rate. And this can lead to thermal runaway, as shown here on the slides. That's an 18650 cell that is entering thermal runaway after being overcharged. So our solution is our ultra-high power cell. So using IP that we have from Kinetic, that we have the exclusive rights to that IP, our engineers have designed a cell with very low internal resistances, which allows for up to 100 C discharge rates. This can increase the rate at which the cells can release their power significantly. Our cells produce more power than anything else on the market, and they allow manufacturers to downsize their engines in their hybrid vehicles whilst maintaining the same performance. So obviously this reduces costs and also improves CO2. So it helps them save money against CO2 legislation by allowing them to produce greener vehicles. So data from the market for lithium-ion cells is pretty clear. It shows a very significant increase in demand for these for lithium-ion cells over the coming decade. This is using information from Benchmark Mineral Intelligence. And even assuming a very conservative portion of the market, our cell presents access to a very sort of significant amount of gigawatt-hour capacity. So the ultra-high power cell has already been making waves in the battery industry. The cell has been independently tested twice at Millbrook, and we're now ready in the pre-production cell for the third round of testing. And we're also working with other firms such as the Southwest Research Institute and Imperial College London. We also work with numerous other universities. Integrators such as Cosworth and Danica have been very excited by the cell's performance and are talking to their OEM customers to utilize our cell in their vehicles. We're also discussing the inclusion of this cell in programs with a number of well-known OEMs directly. So this is already on the radar of major OEMs, and they're looking at accommodating it in their hybrid vehicles. Last but not least, our supply chain is ready. We're already manufacturing these cells in low volume at our AGEN facility in Thurso, Scotland, and plan to scale up through the UK Battery Industrialisation Centre. Our position in the market is quite unique, as you can see here. So we're the only powder-to-pouch cell firm, at least in the UK, but I think likely in Europe. So that means that we work with the raw materials and actually produce our cells in volume, but unlike many other startups that only work with unique chemistries, or the larger manufacturers that only produce unit cells at very high volumes. We operate in sort of the midpoint of that market. And that makes us uniquely positioned to deliver the ultra high power cell and other high performance cells. So our ambitions don't stop there. We're not only looking to double the capacity of our Thursday-based facility, but we're in discussions to build a 5 gigawatt-hour gigafactory that will manufacture the UHP cell and a few other cell variants. And then on an even larger scale, we recently announced news that we were going to work with British Volt to set up a gigafactory in Wales with 5 times the capacity. We've got a very experienced senior management team with over 80 years in the battery experience between them and a history of successfully putting together significant value contracts. In terms of financing, we have a core of long-term private investors who support the business. We have a backlog of grant-funded projects and several privately funded technology development projects to provide a revenue base, and we already have orders for prototype products. So to summarize, our hybrid vehicles are currently limited in performance by lithium-ion cells, and AMT's uniquely powerful ultra-high power cell is an exciting solution, and we're positioned to deliver these cells on a global scale with an experienced team. Thank you for listening. So are there any questions?
Thank you, Fergal. Stephen, Jessica, hand over to you.
Thanks, Fergal. On your value chain chart matrix, I was curious, you mentioned you're dealing with the raw materials in high volume. It sounded like you were vertically integrated, but yet the chart appeared to have you as a cell producer. That's the first part of the question. And the second part is, you have ambitions to scale to a really large factory, but have you substantially validated demand with commercial orders? It looks like you have some grants and it looks like you have some funded POCs, but what's kind of your path toward commercialization and then building out that large factory?
Yeah, so the first part of that question is a fair one. So we're in discussions, so effectively we're setting up those raw material contracts. So the way we went about approaching this gigafactory build is with a Faraday-funded feasibility project to actually test out the validity of approaching something on such a huge scale. It's actually proven very successful. So we investigated 5 sites. We did all the due diligence on those sites. We've now down selected to 2 sites and are looking to sort of break ground on one of them. You're correct. So we have the facility, we would then install lines on a modular basis based on customer orders, but we do have some OEMs queued up who we're already in sort of advanced discussions with to provide cells for their vehicles. So focusing on the UK initially, but we're already seeing demand from Central Europe. So from major OEMs there, especially German OEMs, are quite interested in this as a proposition because we offer something so different from LG Chem and CATL, because we'll work with them directly rather than be a commodity producer that simply supplies down to these kind of customers.
Well, at the same, maybe to challenge that a little bit, but at the same time, these commodity producers are signing contracts with said OEMs for multi-year offtakes. So how do you see that fitting in and with
Sure.
your plans and potentially putting a limit on the growth plan?
Sure. So I think we shouldn't underestimate the sort of capacity available. So Faraday Institute estimates in the UK alone there's 120 gigawatt hours worth of demand for batteries, and we're saying we're going to supply up to 35 gigawatt hours initially. So we're only 1/4 of the available domestic demand if you look at where the car industry is currently. So we're not. I don't think we're overextending to say that this is a supply we'd be meeting. And we are also in conversations on a procurement basis with these OEMs. So we're aiming to supply for the next generation of vehicles. So we're talking 2023, 2024, 2025, or when our orders are coming in. So a lot of the contracts we're seeing at the moment are covering off the demand now, but aren't covering off the demand that's due when higher performing cells are required, especially for these hybrid applications where, as I stated, the current cells on the market just aren't meeting the requirements of these vehicles.
Yeah, And if I can then make a full 180 with the next question is, if you look at the ambitions, like I said, gigafactories going up to 35 gigawatts in the next sort of 3-4 years, what sort of current, what current capacity are you at? Or what's potential doubling of an existing plant, adding 25 gigawatt hours? So if I do my math right, you're currently at 5, is that right?
No, sorry. So to be clear, so our current scale-up plan is, so we have a small batch facility at the moment, which is where we do our prototype small volume runs. And then we're scaling it by utilising the UK BIC, so the UK Battery Industrialisation Centre. They have higher coating capabilities, so they allow us to ramp to medium volumes. So this is how these orders work. So we would supply perhaps 200, 500 battery packs worth of cells. That would be a part of the ramp up. And as our order develops, we will then, our gigafactory will be coming online towards the end of 2022, and then we will be hitting those high volumes. So it's a staggered sort of raise in volume, and that also makes it more feasible than simply saying we're going to jump straight to a 5 gigawatt hour capacity. So then we would have one facility that goes up to 5 gigawatt hours, and then we are looking at this larger facility with British Volt, likely located in Wales if the talks proceed, and that would be 25 to 35 gigawatt hours. And that's one that's been announced in the news recently.
Yeah. Thank you, Fergal. Right, that is our 4 minutes up. Thank you for that. And we look forward to watching your progress. I know you guys have been in the press quite a bit, and the venture community has been following your progression quite intensely. So look forward to see what you guys do. Moving on. So now introducing Markus Mangs, Head of Business for Battery Intelligence, based in Finland.
Hello, hello. Hopefully you can hear me well.
We can, Markus.
Okay, so let me just share the screen here as well then. So hopefully you can see the screen ends as well. It's still loading, but I guess you can see this screen now.
Yes,
we can. Yeah. Your 5 minutes starts now.
Yeah. So excellent. Thank you very much for giving us the opportunity to join this very interesting pitch session. I'm going to take you through very shortly about battery intelligence with our trademark BAMOMAS. So what we do is we focus on industrial batteries and bring intelligence to them. And here I would like to emphasize on the fact that we are not focusing on electric vehicle lithium-ion batteries. We are focusing on industrial batteries. So that's an important note to remember. What are the industrial batteries about? They are often very expensive assets. They are big and bulky. They're being used in different type of equipments, such as forklifts, utility vehicles, even locomotives. They can weigh up to 1 ton, and the price range is between 1,000 and 5,000, depending on size, of course. What kind of problem are we trying to solve? The batteries, industrial batteries, are actually black boxes. They have no information at the moment. They only provide the energy necessary for the different equipment they are used in. So we have a clear problem of lack of information. Also, they are often wrongly used, and that then causes shorter lifetime and also potential liability issues. So the shorter lifetime, the liability issues, lack of information, decreased operational activities, all lowers the efficiency and generates profit loss. So what we are trying to do is to make the operational activities, for instance, in a warehouse or logistics center where, for instance, forklifts are being used, we're trying to make the operations more efficient and therethrough also save costs. Our solution is actually 2 or 3 dimensional. The first dimension is that we have these matchbox sized sensors that measure different parameters from the batteries. So they can measure temperature, they can measure voltage, current, water levels, and so forth. So this is the first step of the process. The second step is that this data that these sensors are collecting, we can send it over Wi-Fi through our cloud-based AI, machine learning-based software platform, where this data is being then processed and analyzed, and you can get really deep and comprehensive information about the batteries and their conditions, and also do predictive maintenance and predict their lifetime and a lot of other parameters as well that generates then potential for operational enhancement. The key benefit is, as mentioned already, that we can expand the lifespan of the batteries. As said, the batteries are very expensive, so our customers don't want to frequently buy new ones because it's a big cost. We can also decrease the maintenance time and efforts by up to 50%, and then enhance the uptime by even up to 100%. So these are the key benefits of our solution. So how do we operate in terms of business model? We have these sensors that we are selling for basically very, very cheap price, the cheapest price on the market, for 35 to 50 euro each. And then we have the key focus, or the key business model generator is coming from the software subscription fee, ranging from 3 euro to 8 euro per battery per month. So this is actually the core and essence, secret of the sauce, as if you want to call it. We are not a hardware company, we are more a software service provider, and so forth. The market verticals where we focus at the moment, or the market segments, is material handling, including forklifts. We have the railways, especially the locomotives that include a lot of batteries. We have utility and golf carts. And then we have actually also different types of other equipments being used, for instance, in harbors, commercial harbors, container lifts, etc. The interesting thing about the market size is that this global battery management as a market is expected to grow to some 15 billion euro in value by 2027. And more interesting actually is that we focus on lead acid and nickel cadmium based industrial batteries, whereas only 10% of these industrial batteries are lithium ion based. And it's predicted actually that this relation 90 to 10%.
Marcus, I'm going to have to jump in and stop you. You've got no time unless you can wrap it up very quickly.
Yeah, so I'm just going to say we have already ongoing 5 different pilot programs. We are just about to launch our own product and expand our sales, and then we are also planning to offer a battery as a service solution, most likely next year. I also have more than information about the P&L projections, and the team is here, very technically oriented team and commercially oriented team. And what we are trying to seek at the moment.
Marcus, I'm gonna have to stop you. Sorry.
All right.
Yeah. I need to give you a question, you guys, a chance to ask questions. So Stephen's probably got questions on this.
Yeah, thanks for not raising the pressure, Chris. Maybe a quick question. I mean, you said you're focusing on the lead acid side, and obviously 90% of that industrial market is lead acid, but we are seeing that people are switching to lithium ion, particularly for the sort of total life cycle cost savings. Do you envisage that your software is effectively helping people make that switch or build that argument?
Well, we at the moment, as said, that we are focusing on lead acid and nickel cadmium, and that market share mentioned 90% will, or is actually estimated to continue being the market share owner for years to come. That being said, lithium ion is also on the uprise, but still in these industrial batteries, it is envisioned to be a smaller part of the business.
But is there anything stopping you from applying the same model? Because effectively it's a sensor, right? So wouldn't that be...
For sure, but the sensor that we have developed is developed for measuring lead acid and nickel cadmium and lithium ion, that needs then a different tool. But yeah, of course we could actually expand into lithium ion as well. But the big market still is going to be for many years to come in the lead acid and nickel cadmium chemistry.
And is the model then to partner with OEMs or to sell directly to the customer?
Well, at the moment we are running these 4 or 5 pilot programs, moving into commercial relationships with them now in August, and then expanding to other customers as well. But we are also looking at, as said, potentially expanding to a battery as a service model, where we would then basically lease batteries and offer our solution at the same time, but also then potentially look at other potential business models.
Okay. So you would buy the batteries from the OEM and then provide them as a service?
That's part of the battery as a service idea, the concept, yes.
Okay.
So we would then basically offer them a more complete package, whereas instead of buying these batteries, we could lease them and include our own solution and service package as an add-on, so to say.
So in that model, what's your risk profile look like? Do you take liquidated damages and the whole responsibility for that?
Well, for sure, that's the thing that we need to take a look into, because it's also about, you know, warranties and liabilities. So, but for sure, in that specific new concept, that would most likely be included, or yeah, sure.
And a scaling question then, I mean, given the value of these individual units is smaller than, say, large industrial, large grid scale assets or EV, etc. From a unit perspective, is there going to be a high customer acquisition cost, or again, can you get around that by partnering with the OEM?
Not really, because we are already running these 5 pilots, and we have seen that there is a clear path from pilot to commercial relationships. And then, of course, using these as a reference, it will be a fairly, I wouldn't call it easy, but it enables us to more easily scale and expand to other markets and customers.
Very good. Marcus, I think we'll have to stop it there because we ran over on the presentation.
Thank you.
So see you, Stephen. Thank you for your questions. And I'm sure, yeah, Stephen will be keen to follow your progress. Right, introducing our next presenter. This is David Brown, CEO of Broadbit Batteries, also based in Finland.
Sorry, I forgot to unmute myself.
Far away, David.
All right. Okay, yeah. So David Brown, representing here Broadbit Batteries, and we have a revolutionary high-performance battery based on common, cheap raw materials. So as you know, in the fossil fuel of today, we use about 1 kilogram of batteries per person, and that's about an $80 billion market for rechargeable batteries. That will soon be $1 trillion market at about 100 kilograms of batteries per person. And existing technology has a lot of problems to scale that much, mostly due to cost, environmental and user harm, charging times, which make them inconvenient, capacity, which, for instance, limits range, delicacy, which requires many of the solutions you've seen before today about stopping thermal runaway and controlling temperature of the batteries. And perhaps the main thing is the limited resources these batteries are made from, namely cobalt and lithium, but also nickel. So what Broadbit has done is we've invented a completely new battery technology based on common cheap raw materials and new operating principles. So operating principle is quite unique. On the cathode side, we use a sodium chloride crystal to store charge. And on the anode side, we don't actually have an anode, but we deposit metallic sodium when we charge the battery to create an anode. And then in between, we have an SO2-based non-flammable electrolyte, so all the issues of thermal runaway go away. And also this electrolyte has extremely high electromobility, about 4 times that of organic electrolytes in lithium ion, which means we also have extremely high power. So there are the 4 main ingredients to our battery: table salt, sand, coal, and sulfur. As you can see, everything is cheap, available, scalable, not controlled by anybody. Supply chains we saw disrupted due to the virus, non-existent with our technology. So in addition to a cost and scalability advantage, we also have a performance advantage. Compared to lithium ion today, which can reach about 260 watt hours per kilogram, we're already at 300 watt hours per kilogram in the lab, and we think we can get above 400 watt hours per kilogram. We actually have recent data to suggest we might be able to reach 500 watt hours per kilogram. So we have a safety advantage because of the impossibility of fire, and also we can fully discharge our batteries for safe storage and transport. This has been verified by a number of customers and third parties. Perhaps the most prestigious would be Fraunhofer Institute of Germany, but also many other institutes and customers have verified. We have 3 patents already granted on the technology and 7 more in the pipeline. This is also a very flexible technology. We can optimize the chemistry for different applications. For instance, we have the high energy version, that's the 300 watt hours per kilogram for transportation applications, electric vehicles. We have a high energy efficiency version, which has over 95% round trip efficiency. We've even achieved 97% round trip efficiency for grid storage and stabilization applications. We have a high power density version, which allows 5-minute charging. That's for things like starter motors, drones, power tools, etc. In terms of the competition, of course, the standard is lithium ion, NCA or NCM, lithium ion. And there's incremental changes in those to make them better performing, mostly by making nanostructured anodes and cathodes to allow higher surface area and access to pores, but that's expensive and hard to scale. Then there's people doing cheaper chemistries, but always at a performance hit. And Broadbit, as far as we are aware, is the only company able to improve performance and reduce costs. That means lots of new applications. We're already working with Airbus for electric airplane applications. We're working with Yaskawa Electric in Japan for grid storage and stabilization applications. And we're working with a company I cannot yet name, still under NDA, for replacing the 150-year-old lead acid battery. In terms of going to market, we're starting with niche and specialty applications already, hopefully at the end of this year with enough funding. That means things like aftermarket onboard units, OBUs in automobiles, uninterrupted power supply applications and drones. We have LOIs on all these applications. Next is the first $1 trillion market, the transportation market, starting with bikes, moving on to buses, trucks, ships, and cars, and then eventually even airplanes. And then the long term is the energy and power applications, so grid storage and stabilization. That's when we've driven costs down with scaling. Our business model is to do part of it in-house. We produce the components ourselves, electrolyte anodes, cathodes, and that means we control our secret sauce. And we outsource the things that other people can do, namely cell assembly and battery pack assembly. We have a very experienced team. Myself, this is my 6th startup. I have about 250 patents to my name. I've raised about 45 million to date. Andras Kovacs is our CTO. He's the original inventor of this technology. This is his 2nd startup. And all of us have lots of entrepreneurial experience and deep tech experience. The only one of us who hasn't started a company is Artem Faustov, but he has also built a lithium ion plant from scratch, so we forgive him. To date, we've raised about 3 million. Our main investor is Yaskawa Electric, but also we've raised public money from the European Commission and Finland. We have some income to date, about 350,000 from samples, demos, and POCs. I can name 3 customers that are not under NDA here, Airbus, Koption, Vulcan, but we have other companies, including world-leading battery manufacturers, automotive manufacturers, and government departments. We're looking for funding right now of around 2 million in the short term to purchase assembly services for our first customers. And then we're looking for another 7.5 million in H1 next year to be matched by the European Investment Bank for first scale up for volume applications. Thank you.
Thank you. Thank you, David. Questions, gentlemen?
Thanks, David. Interesting presentation. So you're planning to keep anode and cathode in-house.
Yeah.
What does that look like now? What does your facility look like?
Well, now we have a facility that can do the whole process, but in very small volumes. So we can make enough, for instance, we can make about 20 liters of electrolyte a day, and we can make about 10 meters of anodes and cathodes a day, which is enough for demos and proof of concept projects, but not really servicing customers. So that's what we're looking for the first money for. We can also make about 10 cells per day just by hand. So yeah, not a lot of capacity right now.
So what does the coating look like?
I wish I had a picture here, but basically black stuff.
No, I mean, sorry, the process. Like, I'm imagining this facility.
Yeah,
and
I
how do
haven't.
you scale?
Yeah, I haven't had. I didn't show it here, but we also have a new process to make the cathodes, a completely dry process that eliminates the use of toxic solvents, and also is a low temperature process, so it removes a lot of the energy expenditures that are normally used for the slurry process. So we basically have a powder that's a bit like Play-Doh that we produce ourselves, and then we run it through a special roller nip to produce the cathode. So it's a very cheap, very efficient method.
So no solvents, basically.
Excuse me?
No solvents, basically.
No solvents, completely dry method.
So in terms of that scaling that up, I mean, obviously funding is one component, but typically the other things is how stable is the how stable is the process to be able to scale up? Like, do you envisage major re-engineering required to sort of get it ready to?
No, the only thing we really have to do is automate the lamination and rolling. So right now we do the process with the same machinery in multiple steps. You can picture it a bit like pasta making. And now we need to buy the equipment that automatically laminates and cuts and rolls for delivery. So but that's standard roll-to-roll equipment, nothing expensive or complicated there.
So from that perspective, there's no new equipment in terms of for any of these steps for automation.
It's just making, well, the new equipment in terms of making it bigger and more automated, but no new design, no new fundamentals, no.
Okay, good. All right. Okay. Thank you very much, David. We're going to have to finish it there because we're slightly behind. And we're going to move on to our next startup. So introducing Konstantin, who is the CEO of G Batteries Active Battery Management Systems. I think I've got it all in there. Konstantin?
Sorry guys, hi. I was on the other line talking to somebody else and I was muted from Zoom. Okay, so let's jump to it. Hi guys. Great to connect. Let's share the screen. Please let me know if you can see my screen.
Yeah, we can see it.
Perfect. All right. Yeah, let's jump into it. So G Batteries, we developed an intelligent active battery management system. Means that we are developed an algorithm that enables us to charge batteries faster without compromising the life of batteries. So a software solution for off-the-shelf batteries. So as you're very well aware, and as this presentation today has concluded, batteries are everywhere in the future. And what we are concentrating today is enabling electrical vehicles to charge as fast as it takes to fill up a tank of gas. And granted, all the vehicles that have batteries today that or devices that would benefit from faster charge, longer life would benefit from our technology. Let's talk about electrical vehicles. So one of the biggest obstacles today for the masses or for the mass deployment of electrical vehicles are cost, life, range, and of course, how fast we can charge the vehicles. Granted, the first three have already been resolved, which is a cost already at par. Life, I mean, warranties are there, not even better than the conventional cars. And Tesla, even Model 3 is giving us quite a bit of range. The speed of charge still remains quite a big barrier, especially for the fleet operators, for vehicles that's supposed to operate around the clock. So let's get into the tech. So why can't we solve this problem in the 21st century? I can hear from the audience that there's quite a bit of knowledge about the batteries. So I'll try to draw a battery 101 and explain what our tech does. a very common graph, retentive capacity versus number of cycles. So on the vertical axis is how much capacity we have, as you very well aware, cell phone, laptop, electrical car. We all start with 100% capacity. As we cycle the battery, charge discharge is one cycle, we are losing that capacity. So for those that are not very much familiar with this, if you compare it to the conventional car, if you fill up a tank of gas in the vehicle, with each and every fill up, the tank would shrink in size. When we get to about 80% of the original size, we're at the end of life. When we try to charge that vehicle or that battery faster, we reach that end of life sooner. So how we envision what happens inside of the battery cell is that when we charge the battery, ions are flowing from one end to another. As we charge batteries faster, we create more traffic of ions on the inside of the battery cell. The analogy here is that if we take a room full of people and ask all of them to run through the same door all at the same time, you can imagine what's going to happen. We're going to crush ourselves, we're going to break the door. That's what happens on the inside of the battery cell. Number of irreversible chemical reactions, from decomposition of electrolyte to growth of SAI layer to lithium plating, you name it. So how can we reach that electrical future of charging batteries as fast as it takes to fill up a tank of gas? What we developed is the tech state-of-the-art hardware that enables us to analyze the batteries or that state of health, that traffic of ions on the inside of the battery cell. Let's call it internal resistance or impedance of the battery cell, and analyze how much energy we can place into the battery in an intermittent state, kind of pulse charging, except each and every pulse is different in size, shape, and form. So what happens is that when we try to pulse charge the battery, you can envision this as we are taking people 10 at a time, letting it go through the doors. Let's say 5 at a time, 3 at a time, depending on the traffic at that door, so we don't crush people, so we don't break the door. That's what we do inside of the battery cell. As a result, we're able to charge batteries just as fast as the red line without compromising the life. And for many instances, especially for the power cells, not so much for energy, but for the power cells, we're actually able to extend the life of the battery at the same time. Filed over 45 patent applications, 10 are granted, 2 are allowed, and many more to come. Started in 2012 and raised 2 seed rounds. We are a YC company. One of our largest strategic investors is Airbus Ventures. We have a great support from Canadian government. We built our own product, which was a battery bank. We built the state-of-the-art hardware. We built the state-of-the-art lab. And we've tested our tech out of the lab from single cells to a small pack. We took a commercial electrical e-scooter. You've seen a lot of those prior COVID-19. And what we did is we actually cut out the BMS, put our own BMS in there, which is in this huge box just for the presentation purposes. And instead of charging the scooter within 5 hours as it is designed by the spec, we charged it under 10 minutes without damaging the battery cell. Where we are today, we are planning to scale this tech from the scooter to electrical vehicle battery pack in the next 2 years. We have a significant support from Canadian government. This project is going to be roughly about $3.7 million. We are looking to raise Series A in the next 2 years. And yeah, so that's our plan. That's our goal. We have a strong team. One of the most important people on our team is Bart Riley, who is the original founder of the company called A123 Systems. He is very much in favor in what we do and in support of our tech. And this is our small team of stubborn pulse charge engineers that are trying to charge electrical vehicles as fast as it takes to fill up a tank of gas. Thank you, guys.
Thank you. Thank you, Konstantin. Stephen, Jesse.
So in some ways, it almost sounds too simple, right? You're essentially parsing out the electrons, or let's say staging them. Why is this not being done already? Why isn't it ubiquitous?
I have the same question to you. Why aren't people doing this? It took us about 8 years to get here. It's not as simple as it looks. It took us quite a bit of effort on trying to manually adjust multiple knobs to be able to get to the perfect scenario, maybe to understand how can we operate at the lowest impedance zones of the battery cells. Even right now, we reached a certain point where human brains are just unable to process all of the data. So we are reverting to machine learning to help us get that and analyze the data and understand when we should turn which knob at what time. So it's not as simple, it's not as straightforward, but definitely something that people have been doing since 1970s on lead acid batteries. Pulse charging is a known fact to work great. There's a number of companies out there that are doing modulation of current and they're achieving better results in the battery cells. So why it's not widely used, I don't have an answer for you at this point. Definitely something to look into. How do we protect ourselves from others jumping all over it right now? We have a pretty strong IP portfolio at the moment and quite a bit of knowledge on the batteries over the last 8 years that we've developed directly with hands-on work that we put into it.
Constantine, I have a question for you. So how much testing have you done on your protocol and your system? Like you showed an example there. We charged an e-scooter in 10 minutes. Have you tested the cycling numbers that you posed in the previous graphs?
Yeah, tens of different battery cells, from jelly rolls to pouch to prismatic to cylindrical of different shapes, different chemistries, different electrolytes, tens of different batteries, tens of thousands of hours, tens of thousands of cycles. We do not do approximation and modeling because what we do with the batteries, you can't really model it because we are triggering different reactions within the batteries. So we, excuse me, we actually had to run through thousands of cycles to get to the actual end of life of the batteries to be able to get that data. So yes, thousands and thousands of cycles what we've done to date over years.
So you have simulated end of life systems. Okay.
We did not simulate it end of life. We actually got to the end.
Yeah. For the clarification.
And you mentioned the scooters, so that's more of that was an AC charging solution, or was that DC charging, or I guess it doesn't matter for you guys?
It doesn't matter for us at this moment. So we just cut off all of the BMS and we just use our charging approach. So we were doing this modulation of energy going into the scooter. But what's interesting here is that in the lab, we control individual battery cells. In the scooter, we control the full pack. So that was a kind of the first step, a huge step of scaling. So now we'd like to scale it to the pack and see how can we scale it to like 8,000 cells of a Tesla battery pack. It's a big challenge. Of course, we have solutions, we have patents, but can we do this? This is something that what we're looking into. Right. But for the cars, it would be DC charger, absolutely.
Yeah, and in terms of the, just maybe one thing, you mentioned, you used the analogy of the door and sort of 40 people running at an exit. I mean, yes, if we all queue up nicely, then you can get more people out. But at some point, you just still run into the physical limitation that you only have one door and you need to get 40 people out. So do you have a sort of rule of thumb in terms of what the scaling factors of the benefit that you're able to achieve? Like, is it 5 times, 6 times, or at what point do you actually start running into, again, hardware and other issues?
Very good question, and absolutely physical limits are still at play. The higher energy dense battery cells, there's limits, and we reach those limits much sooner. For more power cells, for example, with the scooter, they use power cells. So we were able to go scooter charge within 5 hours by the spec, but really you can push those batteries to about 40-45 minutes CC/CV charge, no problems. So we did 10 minutes, so that's about 4 to 5 times improvement on the rate of charge. Is the energy cells right now we're looking anywhere between 2 to 3 times improvement so far from the spec, and energy cells are definitely harder to reach. But the bottom line here is not how many times better; it's what is the requirement. So if you only want 100 cycles, you can push even the energy cells to further. So it's really depends on the requirement, cycles versus rate of charge. It still works just like today, except we're able to take that rate of charge to the next level.
Thank you, Konstantin. Appreciate it. I'm going to have to interject at this point and move it along. Right, so next I'm introducing Andre, CEO of, I hope I pronounced it correctly, Geyser Batteries. Far away.
Hey, hello all. Thanks very much for Conferring Ventures to group up this nice team of startups and investors. So we are Geyser Batteries, a Finnish company, and we are scaling up adoption of our novel batteries, differentiating in their heavy-duty performance and very high sustainability. Our focus is the applications where a battery needs to withstand tens to hundred thousands of deep discharge cycles, preferably high power. So this is a new class of batteries, and it is built using our own proprietary electrochemistry. We have managed to combine supercapacitor and redox battery in the same electrochemical system. And we did this not by substituting one of the electrodes with a battery type electrode. It is still two carbon electrodes, and the reaction happening is in electrolyte near the surface of electrode. So this presumes high performance of supercapacitors, but adding multiple times higher energy to the system. Importantly, this is water-based, so the system is very safe, and apart from the high safety, it is also a low capex manufacturing that these batteries are enjoying. So we are excluding very energy-intensive manufacturing steps compared to lithium-ion and supercapacitor batteries, and this makes us also very low carbon manufacturing process. For typical applications like hybrids, opportunity charged machinery, power grid stabilization systems, our batteries deliver times higher power over 10 to 100 times more discharge cycles compared to the best high power batteries. And they deliver times higher energy than the best supercapacitors that you can buy. I'm a PhD physicist that has followed entrepreneurship and industrial business development path, and we started this company 2 years ago with my partner Alexei Belikov, who is an energy storage industry veteran with over 40 years of experience. Through these 2 years, we have strengthened our team with great professionals, very passionate about what they do in the manufacturing space, in business development, sales. And now with this new funding round, we are bringing in a new CEO, CFO into our company, and also Chief Commercial Officer. So our passion is shared by our strong advisory board, and we are looking to expand this as well with the new financing round. Some of our products are in operation for over 2 years now, so the tech definitely works, and we're busy adopting these products for early use cases, which tend to happen with OEMs. They are a bit more forward-looking, but tier ones are of course very interested, and they, however, in a wait-and-see mode. So they're waiting for us to scale up our manufacturing process, and that's what we are working on right now. By end of this summer, we are delivering the core assembly node, which will be essentially a cells assembly node, and that's a heart of our manufacturing line. Further on, we will be scaling the manufacturing, but we will be switching to the licensing mode to ensure the multiple supplier situation for our customers, and also just simply to be able to produce more. We use platform approach to development of our products, and currently we're envisaging 4 product lines. They are different in their functional parameters, like power, energy, cycling frequency, and cooling requirements. We have just finished the first product for the first product line, and we're now working on a product for heavy machinery hybrids and for high frequency onboard grid stabilization. These are customer cases opened all across Europe, and each of them is going to bring us 50 million plus sales opportunities, but most importantly, they build foundation for the product line addressing billions worth industries. We're in fundraising mode. Our current investors include 2 VC funds. One of them is actually backed by Finnish National R&D institution, VCT, and we're also backed by a family office of Andrews family, the oldest industrial family in Finland. We are very much in line with EU agenda, so new investor may expect strong public co-financing, and we're looking to raise a round to scale sales in the hybrid sector with this product that we're finalizing now, complete commission and certify the automated production line, and of course to keep innovating. Hope this describes the situation.
Thank you, Andrei.
Thanks, Andrei. compared to something like a Maxwell, sort of the incumbent super caps, how do you position yourselves, and what do you do, for example, on cooling that's differentiated?
Do you still see my slides?
No, just you so far.
Okay. So basically, first of all, we differentiate ourselves to Maxwell in the amount of energy that we can put into our battery modules. It's up to 5 times higher energy density devices. They're also, as we start the automated manufacturing, approximately half the price. So the manufacturing process is very simple because of the aqueous electrolytes that we use and the simplicity of materials that we are employing. And in terms of cooling, I think it's worth mentioning here, and this is an important part of our IP, that we use bipolar design, which is basically just boosting the power in the system, but also makes everything very planar. So cooling of the system is very easy, and it happens very evenly, which also extends the lifetime and also helps with the recycling.
Stephen, do you have any questions?
There was a bit of a lag here briefly. No, I think that's right.
Okay, all right. Well, in that case, we'll try and make up a bit of time. Andre, thank you very much for that. And we're going to move on to Raphael Meyer, CEO of NEC Energy Storage, based in France.
Hello, everyone.
Hello.
Hello, can you see my screen?
We can.
Perfect. So I'll go ahead. Good afternoon. I'm Raphael Meyer, the CEO and co-founder of NEC Energy Storage. It's a young SME based in Grenoble, France. And today I propose you to build a world of prosumers by combining high efficiency and as a service energy storage. You might know that in Europe, here we go. You might know that in Europe, the heating of the buildings, it's more CO2 emission than transportation. And in some other regions, AC systems, that's the majority part of the national electricity consumption. And that's why we need urgently a new generation of HVAC systems. And we do think that energy storage is the key asset for this new generation. And that's why we have developed embedded energy storage product, which is for us the best way to leverage the benefits of storage for the people. It's an electric radiator with a battery storage inside. It's an exclusive solution, 11 patents families. We were awarded by a Best of Innovation, granted by SME Phase 2 last year, a New Energy Challenge, as well as a Solar Impulse Efficient Label. It's a system that is smart with different sensors linked with the smart meter and self-learning algorithms, the idea being of having an autopilot 3D performing for the heat generation. And then, of course, we have a storage, a battery of 800 watt-hour in each device. Then just imagine that you have 1 to 2 devices per room and that you will aggregate those divided storage capacity. We also add a 500 watt microinverter in each single device to re-inject into the grid. And with this configuration, we think we have the perfect self-consumption bundle. For instance, 7 radiators with a total storage of 5 kilowatt hour, and that can manage 6 kilowatt peak of photovoltaics in self-consumption the whole year. You can use a fresh battery, of course, with a pretty amazing cost of 250 euros per operating kilowatt hour, I mean in AC, but you can also use a second life spike battery. And as we know, it's a world premiere as we do it without remanufacturing. So it's very, very cost effective, and it also allows to reduce the footprint. It's a project we're pretty proud of that we've developed with Groupe La Poste in the Paris area with 10,000 electric bikes that will give their batteries in second life for our stationary storage. And as a result, we have today the cheapest storage solution if we talk about the operating kilowatt hour. And as a result, we also have the shortest return on investment for a storage system, imagining the whole bundle that we can propose to our customers. Fast return on investment, it means that it's pretty logical, actually, to propose it fully as a service. And that's what we are building right now with our partners like energy suppliers. The idea is you subscribe to our offer, you have no investment to put onto the table, you have the hardware, I mean the photovoltaics, our system, the installation for free without investment, and you will buy just the electricity that is produced on your rooftop. And that's a system that is feasible in terms of business model if you add the recurring revenues that you can make with the battery that you have onto the grid with the grid services mechanisms. And we are already active on this topic with the Smart Grid Energy in France. With this value proposition, we could already replace the 150 millions of space heaters that are deployed worldwide. It's a pretty nice market. And if you add, of course, the battery storage market, then it's pretty nice in terms of development until our air conditioning system with batteries is ready. To achieve this ambitious roadmap, we have 30 people based in Grenoble, in different fields of expertise, and different main partners that we would like, of course, to enlarge, like EDF, ENGIE, Groupe La Poste, Stelpro. It's a leading manufacturer in Canada, and we will start a licensing agreement with them in the coming years. We started this adventure in 2016. We've put our first products onto the market in 2018. Last year, we were granted by SME Phase 2, and we finished successfully a Series A fundraising of 7 million euros with ENGIE New Ventures and Stelpro. This year, we have done our first operations in self-consumption. By 2021, we will propose our first as-a-service offer in France and other European countries, and as well as the first introduction of second life bike batteries in our battery fleet. And finally, by 2022, we're going to have the first sales in North America through this licensing scenario that we would like to generalize also in Europe, as well as the first introduction of air conditioning system powered by Lancé. We will reach profitability by next year and 10 million euros of net revenues by 2023. Will we build an electric future? Actually, it depends on you. Thank you very much.
Thank you, Raphael.
Thanks, Raphael. Where's the core of the IP? It looks like you're integrating a substantial number of components. And so are you...
That's correct.
Is there a software IP in the control of all this, or what do you...
That's correct. It's indeed definitely a system. We are pretty far from the, let's say, a material R&D for our electric chemistry. But still, if you want to make within the same device, which is not that big, a battery, a microinverter of 500 watts that is that fulfills the electromagnetic certification, that is safe to use, that is in terms of thermal management control. As you know, the battery doesn't like to be heated, and actually our system is a heater, basically. So of course we have different kind of way to protect this in terms of architecture. So we have a couple of IPs on this. The way to reuse, pretty simply, a connected battery with a connected BMS from the bike to the radiator without remanufacturing is also something that we have protected. And the last patents that we have are more, let's say, fluid patents on the AC system that we are actually working on in R&D. Actually, part of our patents are available. Some are public already, so you can just take a look and see where the IP. But let's say it's an architecture, thermal management system, and the power electronics mainly.
Speaking of the batteries that are being reused from bikes, assuming people don't cycle enough and there's a limited supply from that particular OEM or application, can you easily integrate other sources of second life batteries into your system?
Yes, very good question. Indeed, we are pretty actually agnostic in terms of electrochemistry. So to date, what we use is Samsung SDI because they are pretty good cost ratio, quality and cyclability. But we could use actually many of other technologies. Actually, what we need is just a voltage. The rest, actually, we don't really care. Indeed, what we are doing right now with La Poste is pretty simple because it's one owner of the 10,000 electric bikes, and we make the arbitrage remotely which batteries have to be replaced, and we decide actually. So we select the batteries that are, let's say, just good enough for a second life, but not too aged. And in this case, we cannot do anything about this. If we want to scale this model, it's a bit more complicated. So that's why there's still a lot of things to do. But what we want to do is basically send you the notification if you give back this battery, you will get, I don't know, 100 euros, 150 euros if you bring back this battery now. But if you wait in 6 months, maybe your battery value will be 0. So the idea will be to include the end user within this selection process in order to really optimize the lifetime of those bike batteries. We have any way to select them. If we just let the end user decide, actually what we will recover is something to be recycled only. So we have to act a bit in between. But this has been shown in the slides. As you know, with lithium ion, you have a plateau of aging, and then it drops dramatically. So we have to stop when we are still in the aging plateau, and that's exactly what we do.
Okay. And so you say, oh, go ahead, Jesse.
Just a quick one, thanks, Stephen. The business model, I didn't quite catch it. So you're doing the PV and storage in-house for free.
Yeah.
So battery as a service, and then how's the revenue from grid services divided up?
It depends on the country. If we take the example we know the best, which is France, if you add the fast containment reserve, which is the most difficult grid services to do, so the frequency alignment, it's about 50 euros per year and per battery. And if you add all the flexibility mechanisms, you add maybe 15, 20 euros, depends on how strong is the winter actually in France. So it's up to 70 euros per year and per battery that we can generate today with this capacity and with this power of bidirectional flexibility. So it's not that much actually. It's not self-sufficient as an activity, if you will.
Then you're just using the capacity of the battery or the capacity of the whole system, because technically you've got some flex in the heating as well, right?
That's correct. Well, of course, there is a bit in between zone where you can play on both, but normally you're not supposed to, because what you do must be perfectly symmetric. And there is also something that has to be taken into account. It's the comfort of the end user. So, and we don't want to. We want to keep the user acceptancy maximum. So normally, what we do, if the global management system is correct, is just playing with the batteries, and to some extent, so basically a delta which is pretty smooth in terms of reference temperature, we accept to play also with the heating bodies. But
so would you say there's something proprietary on that level of control as well in terms of how you aggregate that, or is that primarily managed by the third party who's giving you access to the market?
Exactly. What we do is a kind of marketplace. We we have a PhD on this, but it's not the part of the business we want to be involved with, because there are actually plenty of grid aggregator, and we don't think that it's the right place for us in terms of just how we can disrupt this. So basically what we do is each year we put onto the market our storage capacities, and we select what kind of aggregator can propose us the best rate. And then actually we are developing an offer with NG in France, and we are actually interested in building a similar offers with other energy suppliers. We had a couple of discussions with some of the, sorry.
I'm gonna stop you. Yeah.
Sorry for this.
Thank you.
You can send me the question by mail. It's a pleasure.
Yeah. Maybe you guys can communicate after this. Yeah.
Yeah. Thank you.
Thank you.
Okay. Next, I'm introducing Brian Morin, CEO of Stoteria Battery Innovation Group. I hope I pronounced that right. Brian? There you go, Brian.
You can now see my screen and hear me?
We can.
Okay.
Time starts now.
Good. So my name is Brian Morin. I'm CEO and co-founder of Stoteria Battery Innovation Group. The simplest way to tell you what we've got is to show it to you. What we have here are state-of-the-art lithium-ion cells. The one on the left is traditional. The one on the right has our aluminum current collector in it. These are about 240 watt hours per kilogram. And you can see the difference is simply the traditional materials, when you do this nail penetration test, turns the battery into a flamethrower. Our cell continues to work. Actually, the only place where the cell is not functioning is right around the nail. The rest of the cell continues to function. We pulled 93% of the energy out of this cell after the test. Our goal is to eliminate fires in lithium-ion batteries forever. We're not going to do this by ourselves, so I'll talk to you about how we're bringing the rest of the industry along to do it. Three pieces to our story. The first is the revolutionary safety. The second is that we do this with no compromises. So there is a 20 to 30% weight reduction as well as material cost savings. And then we're doing it with a lot of industry support. So a few seconds of technology. Every lithium-ion battery fire starts when something punctures the membrane. That generates heat as the energy of the battery is dumped into that spot, which shrinks the separator, which causes more energy to flow, more shrinkage, and eventually goes into thermal runaway. We're doing two things different. The first is to replace that plastic membrane with a nanofiber-based non-woven separator, which is made from traditional fibers on paper making equipment. So it's relatively inexpensive. It's reinforced with Kevlar, which is stable to 500 degrees Celsius. So it's never going to melt or shrink. The next thing we do is replace the metal foils with metallized film. So think a potato chip bag, thin sheet of plastic with enough metal on each side to run the battery, but not enough to support the large current densities that would light it on fire. Now, when you get the short, the energy dumps in, the separator chars, but doesn't melt or shrink. And the current collector now pulls back, burns out like a fuse, stops the flow of energy, and you're left with a dead spot in the middle of what is otherwise a completely functioning lithium-ion battery. We're going to have our biggest impact in electric vehicles, but it's the wrong place to start. So we're starting in everything else that either moves or is carried. And we're doing this with an interesting model where really everybody else does the work. So in one case, Applied Materials made the material. The material was delivered to two fine Chinese battery companies who've made cells and delivered those to end users. We're replicating this model, and I'll talk more about that. Competition today is largely steel boxes and solid state batteries and non-burning electrolytes are coming, but neither one of them is at scale or able to deliver the function that's needed. We have two large intellectual property patent portfolios. The separator has 53 issued patents. The current collector, filed much more recently, has 7 applications with 2 issued patents. We're taking everything globally. Our business approach is a copy on the Bluetooth business model. So we've formed a consortium now of 68 companies, include the ones you see here, but Mercedes, Bosch, Teijin, Motorola, and you see the others. The consortium has 3 goals. The first is to set up a supply chain that's adequate for the electric vehicle and battery industries by licensing the material to the best advanced materials companies out there. The second is to set a set of uncompromising safety standards at the cell level. And then the third is for cells that can be certified to those safety standards, whether using our technology or not, use our mark to denote the safety that's inside the cell. So whether somebody's buying a power tool or a cell phone or an electric vehicle, if it's got that Soteria mark on it, they know it's safe. This shows the consortium members split throughout the supply chain. So you see we have go all the way from material to end users. We have 3 sources of revenue in our business model. The first is membership fees, which were $200,000 in 2018, $480 last year, and over $600 this year. And then the rest comes from licensing upfront fees and the ongoing royalties, which is where you get the larger returns later on. Several exit options that I'm going to skip because of time. A good team, everybody has advanced degrees, everybody has both large company and entrepreneurial experience. Our advisory board, I'll highlight just a couple. Brad and John are more than 10-year senior execs in lithium-ion batteries, and Randy was a direct report to Jack Welsh. We've won several awards. We're raising $2.25 million. We're about a third of the way through that, led by the Keiretsu Forum. And with that, I'll pause, I think, on time.
Thank you.
Brian, thanks for that. Very interesting. I was just a little curious about the competitive landscape. The steel boxes and titanium plates seems a little bit of an oversimplification, right? There are some ceramics that are being explored, for example. I know of MIT efforts, for example, looking at ceramics for dendrite arrestment. So how do you really characterize your competitive landscape?
Yeah, sure. You got the 10% of 5 minutes version of competitive landscape there. So today, a lot of the safety, and the big difference is most of the safety that you see out in the field today is built in at the pack level, not the cell level. They presume unsafe cells. And you saw earlier, Jenna's approaching this from a different perspective. Theirs is very good, right? So we're both trying to build in safety at the cell level. Today, they presume unsafe cells, and then they build in insulator, switches, boxes, everything else at the pack, the module and the pack level. That amounts to 30% of the cost and 30% of the weight of lithium-ion batteries. If we can improve the safety at the cell level, it allows them to take out weight and cost at the pack and module level.
Thanks.
From customer perspective, I can just confirm that it's a great product. Thanks very much for that, Brian.
Thank you.
And you mentioned the consortium and all that sort of stuff. Is that a loose collaboration, or is that actually a requirement? Because you mentioned, I mean, do you need everyone involved in order to make the changes in terms of getting people on board, scaling up the technology, etc.?
Yeah, so we've put it out as an open innovation platform within the consortium. So in order to have access to the platform, that companies need to join the consortium. Once they're there, then it is kind of a loose set of projects that any company in the consortium can work with any other company or set of companies within the consortium. We have at this point about 70 projects going on between the different companies, primarily funded by their own internal R&D dollars. Some of those we get to track pretty closely. Some of those the companies keep confidential, and we only get kind of, requests for material and loose feedback. And so we're kind of the IBM PC model of how we're approaching the industry, right? Which is to put it out open. The requirement where we get our revenue is the actual material producers, the component producers of the separator and the current collector will pay us a royalty. Everybody else just sees them either as a customer or a supplier.
Okay. Why go through that hassle and not just have a straight up licensing model?
Well, in one sense, it is a straight up licensing model, but what this does, it brings a fair amount of revenue forward. So I like to pay the bills, and I'm not, and honestly, revenue is an old friend. I miss her. I'm glad to welcome her back. And truthfully, we would like to be a cash flow positive company as fast as we can, because if we're going to maintain a standard for the industry, we can't be going from A to B to C with the chance of failure each time. Right? We have to be a trusted entity within the industry. Even if our technical technology fails, if we're going to maintain the standard, we've got to be around, right? So.
Okay, thanks.
Thank you, Brian. That's perfect and on time. So I'm going to draw questions to a conclusion now. And I'm going to welcome our last startup. So this is Talat Azad, CEO of Store Electric Limited, based in the UK.
I guess hopefully you can see me.
You can. Fire away.
Okay. Okay, is that visible to everyone?
It is.
Great. So I think we decided after we saw that we were right at the end that we would change our name to Aardvark Batteries. That way no one can precede us in the future. So my name is Talat Azad. I'm the CEO of Store Electric. And I'm going to touch upon four things. First of all, why large-scale storage, the technology portfolio that we've got, the business, both in terms of IRRs and the projects we're looking at, and then what's next. I start with basically this graph, which is from a UK government organization looking at different countries in Europe and also in the US, and it shows the amount of storage required as you get more and more renewable energy deployed in the grid. And you see that around about that 50% level, you probably need about 10 gigawatts of storage. But as that increases, you're getting to the levels of 30 to almost 50 gigawatts. And that's something that just can't be done with small scale storage. It needs what we call baseload or large scale storage, but not just with short durations, with long durations. And that basically is what Store Electric is looking at. But in addition to renewable deployment, you also have instability in the grid. So this is basically a picture from the national grid, the system operator, that shows what happens to instability in the UK as more and more renewables are deployed and as conventional plants are decommissioned. And all the white spaces are basically areas of instability. And those gray bands that you can see are basically locations where the geology is suitable for our technology. So basically a massive potential. So basically renewable energy deployment cannot continue without large scale storage. That was basically our finding about 4 or 5 years ago. And we said that there was a massive hole in the market for proven, reliable, cost competitive and large scale storage technologies and projects. So we're both a developer of the technology and a developer of projects. Now, how does CASE work? Basically, CASE takes energy from the grid or from a renewable source. It uses a compressor to compress that air underground in a salt cavern or alternative underground storage. And then in the evening, when it's required during the peak times, that heat is then released through an expander to generate electricity. Now, we have three basically areas of three technologies in our portfolio. We have one which we call diabatic case or CCGT case, which is like a combined cycle plant, but with storage attached. And that would generate efficiencies of around about 50 to 60% compared to 42% of the first plant that's been running now for about 40 years in Germany. We've got three ranges, 75 to 640 megawatts. That also can use hydrogen as well as methane. So that solution can also be completely 100% emissions free. The second solution is what we call adiabatic case or thermal energy storage case. That uses the heat from compression, stores it, and then uses that when we want to generate electricity, achieving efficiencies of 63 to 68%. Now you can combine those two together to produce what we call the hybrid, and then we're dealing with efficiencies of about 75 to 80%, but also with a lot more flexibility attached to these designs. So we can attract probably up to 20 different revenue streams. We can reuse equipment to help sustainability. And actually our solutions potentially can also be negative carbon, but I won't explain how we do that. In terms of competitivity, you can see CASE here. This is basically a report from Energy Catapult from April 2020. So that's a few months ago, that shows CASE is by far the most competitive solution. Our own CASE solution would probably be 2/3 of that figure. And we will remain competitive for the foreseeable future compared to the other technologies, which in some cases still have safety concerns. Let's have a look at the internal rates of return. If we take our middle range plant, we would achieve an internal rate of return of about 12% based upon price curves from Baringa. This is an energy consultancy. If you hybridize that solution, we're hitting 16%. And assuming a 25 to 75% debt split, 5% interest rate, that's a 50% return on equity. I don't include those items on green on the right, or red, or black. All of those would further enhance the internal rates of return that we're talking about here. In terms of locations, this is the UK. We have a lot of generation, offshore wind generation in the north. We have a lot of demand in the south. There's a bottleneck in the middle. Our plants basically that we're looking at are located in this area here. The first of these projects, projects 1 to 3, we've actually already done the habitat surveys for those. Projects 4 to 5, 6 to 7, 8 to 10, all of these are locations that we've already started speaking to the owners of the caverns for, and they have existing caverns there, but they also have the potential to solution mine more caverns. So each of those locations is an area where that white space was that I showed you earlier. And very importantly, the potential to have multiple projects there is very, very high. This is basically the team, and it consists of 3 of us in terms of the main team, and we have a number of advisors. And we have a number of different companies that we have collaboration agreements with that help us on the project development side and project execution side. In terms of what we need £5 million right now to start and get it to construction ready or financial close for the first project. And 2 million of that 5 million would be for additional project development. And then 75 for the first build. And the use of those funds would be for the management board, for more engineers, and for financial close of that first project. And I think I'm more or less complete.
You are indeed out of time, Talat.
Okay, I think I'm done with that.
I'll hand it over to my jury. Stephen,
I think yes, he's talking, but he's on mute.
Yeah.
Sorry, I'm an amateur quarantiner. No, thanks. Interesting presentation. I was just curious about the UK market, which you point to, which is increasingly an inertia problem requiring fast response, but you're attacking more or less a duration problem due to intermittency. Do you think that your markets are near term, or when do you think that you really start to show positive traction or substantial traction?
Well, on the one side, I would say that the National Grid, the ancillary services that you mentioned, they've already started new initiatives to address things like reactive power compensation and also inertia. So the first of those tenders came out in December last year, and they're expecting to be rolling those out over the next year or two. So from that point of view, I think we're already in the right place at the right time. And the tenders that did win contracts previously were all synchronous machines. They were rotating machines, which is exactly what our technology is. So, and there's a lot of plants in that area that I showed where you had that rectangle, where there's a lot of decommissioning of existing fossil plants. So you've got a situation where there's a lot of energy coming in from Scotland, existing plants are being decommissioned, and they need rotating mass in that area. And that's exactly what we provide.
So you're maintaining a baseline of rotation, basically, and then when you're called upon, you essentially just ramp a bit, but you've already got that rotation inertia in progress.
Yes, I mean you can work slightly different. You can work different ways. I mean, on the one side, we could have the plants basically running not for the full duration, because part of that time we would be compressing. So for about 7 hours, 8 hours per day, we're probably compressing, but for the remaining time, we could be, let's say, on standby. But at the same time, we've got this additional flexibility built into the design that if we wanted to decouple the generator from the turbines, then you could use that generator as a reactive compensator as well. So in other words, provide voltage support. And I think that's a really important point, that if you can build that flexibility in, and there's a number of different areas of flexibility, you can to some degree mitigate the regulatory risk, which when markets are deregulating and lots of changes are happening, you really have to address in some way. And I think our solution addresses that. But I also think what we have as a solution is something that's required right now.
And then so the practicality of going from, would you say, about £5 million now to just kind of build out your R&D roadmap to something like £75 million for your first build out. I mean, can you point to examples where that jump is made? I mean, if it's project financeable, that's one thing, but is there not a more programmatic approach that makes sense, that's more realistic to get you to your build out?
Well, what I would say on that, there's a couple of points, and I think that's a very good question. Firstly, what we've said and we've sort of maintained is that the actual technology itself is pretty much proven. So there are two plants that are running. One started in 79, the other one in 91. 91 is in the US, and they're still running. So the technology itself, conceptually, is proven. What we've done with the technology is, you could say, enhanced it, built in more flexibility. So there's not really more R&D work that we need to do. What we've done over the last 4 or 5 years is basically done, and that's been validated by fairly large engineering companies like Siemens and Costain. So we're really at that point where we're now looking at the rollout of that technology. The 5 million is really only for really the first plant would require a little bit more work than the subsequent plants, because it's pretty much the same thereafter. But going from that to 75 million for us is not really a big step, because the technology is proven. The actual supply market is already there. We can get the equipment from pretty much all of the OEMs, whether that's GE or Siemens or Mitsubishi. And because it's essentially like an existing power plant, the risks are actually quite low, which is one of the reasons why Mitsubishi now has agreed on our first project with EDF in Cheshire in the UK to actually take the EPC responsibility for that.
So that's not proof. I mean, proof is you have a bank that says, look, we understand that the Alabama plant, the Dresser-Rand plant is, functional for years, and the one in Germany, the Siemens plant. And the banks say, okay, we get that risk profile, and we're ready to do project finance at a certain capital structure, approaching a renewable project, maybe 40-60, maybe going toward 30-70 or something like that. And then this looks like an equity chunk of maybe 30% of 75 million rather than 75 million entirely.
Well, we're actually talking right now to probably 3 pension funds. That's we're at different stages of development. So that's jointly with our friends from Mitsubishi, so together. One of those companies has actually already said that they would be willing to finance the first project, and their view is that with it being the first project, it's a very large pension fund. What they've said is that that first project probably is going to be 60 or 70% equity, and the other 30-40% shareholder loan, because it's the first project. So they're willing to do that, and they've said that they would be subject to us getting the planning permission secured, getting the grid connection secured, which is part of where the £5 million will be going to. They would finance that first project. But I think one of the reasons that's in the back of their mind is that that solution, once it's built and running, that's going to have a lifetime, not just of 25 years, which is how we've modeled it, but more likely 40 years. You know, and there's a pipeline of projects behind that, which particularly for pension funds who are probably looking for 5 or 6% return, that's a fantastic opportunity. Now, in the UK specifically, I think one of the things that they've thought was very important is that the actual underground storage that we're using is existing caverns. We're not solution mining new caverns, which would take a bit more time to do, would be more expensive. But at the same time, and one of the things I sort of very briefly alluded to, is that we can use, because our solutions are essentially standard, unlike the 2 plants that are running where it's not a standard gas turbine, it's a modified gas turbine. We're using standard gas turbines, which means that we're open to any of the OEMs. But more importantly, and this is my background, I used to work for Alstom before as sales director for their EPC business. There's a lot of gas turbines that are basically sitting out there doing nothing at all. So the opportunity for us to be able to reuse those and basically reduce our capex probably by another third is very, very high. So that sustainability dimension, the fact that we're pretty much emissions free or negative carbon even by doing some other things, which I don't go into.
I'm gonna have to.
If I can just squeeze
one in. I
encourage
you, Jesse and Stephen, to potentially follow this up further, because I know Stephen's probably biting at the bit to ask a question actually on this. Running one of the larger front of the meter battery businesses in the UK. So look, I'm gonna have to draw things to a close here, but if you guys want to carry on after this, then I'm sure you guys will be able to do that. Thank you. Yeah. All right, guys. Look, so just to finish things up, thanks for the time. I know we've had a 2-hour marathon there. So thank you to the jury, Jesse, Stephen. Thank you to the startups, and join us, and thank you to the live audience as well for those that are watching. And just to remind everyone, there's going to be our next track in digitalization tomorrow at 3 p.m. Central European time for those who want to tune in for that. So until that time, thank you all, guys, and we will be in touch soon.
Okay, thanks.